Good afternoon and welcome back to you all for this hands-on training on machining process simulation using Deform 3D software. Okay, first I split this into two different things. First, in the first one, we will see the two-dimensional machining process simulation, and then we will move on to the three-dimensional machining process simulation. So in this software, we can do simulation studies of turning, drilling, milling, boring, ring rolling, then forming process we can do by using Deform 3D software. First, I'll start with 2D. In the 2D, I'm going with the machining. So Deform Mac 2. So here you can see Deform Machining 2, that is two-dimensional version 10. So first, File, New Project. So this is the front interface. So in this, I'm going to give the project name. The project name I'm going to give is AAER. Okay. So the name that I'm going to give, and here I can give any things. Okay. Parameter study. So that's up to you to provide. Then the unit system here we have is two. One is English, that is feet. Then SI systems. Normally, we consider and we follow only SI units. Okay. So I have to select it as SI. Then next. So it considers it as operation number 1. Okay, leave as it is. Here you can see the type. It is machining transient. So in the morning session in the PowerPoint presentation we have seen that is first we will be simulating the machining process in transient conditions. That is, it is a dynamic one in which the variables vary with respect to time. And after reaching or after obtaining some subsequent chip formation, we have to make some modifications in the chip, and then we have to convert that into steady state condition. So initially it will be in the transient condition. Upon modifying the chip, then only we have to enter into the steady state condition. So in the top you can see the process setup, process condition, tool setup, geometry, coating, mesh, everything and all. So we have to follow a sequence. We cannot omit, otherwise the database cannot be created in this. So machining transient, click next. Now I am going to provide the cutting speed, feed rate for this. So if I am going to consider the rotational speed, then it is RPM. So I have to select the workpiece diameter. Why RPM? It is asking for workpiece diameter because it is pi dn, V is equal to pi dn by 60. That is the formula that is associated with the cutting speed, right? So for cutting speed, what is the rotational speed? N. So for this, it requires the diameter of the workpiece. So I am going to have with this surface speed, that is the cutting speed. So here I am going to consider it as 200. It's just an example of how to work on this software. Then feed rate, I am going to retain this as 0.1. Then next, the environment temperature. Because here in this case, we are going to determine the temperature that exists at the interface. That is at the interface of tool workpiece, tool chip and workpiece and chip. So three interfaces are there. And also how the heat is dissipated, that can also be seen in this. So for this, we require the atmospheric temperature. So I am going to give it as 30. For example, I am going to give it as 30. If I am going to do an experiment in a real-time conditions, now it is the summer. The temperature will be around 33, 34 or 35, 36 also in some conditions it will be there. So if I am going to correlate these machining studies, these simulation studies with the experimental studies, then first of all measure the atmospheric temperature presently and give that temperature here. So for example, I am going to give it as 30 degrees centigrade. So here you can say C, this centigrade. So tool work interface. So what is the friction factor? What is the heat transfer coefficient? So these and all things, it depends on the work and tool material that we are going to select. So how to select these values? From the previous literature, for example, if I'm going to consider a titanium alloy, titanium grade 5 alloy or Inconel 800. For that, if I'm going to use a coated or an uncoated carbide tube, some researchers have carried out some experiment and they might have presented their research in a manuscript. If they are considering the shear friction factor and heat transfer coefficient of that, you can just take it away. Okay, if I am seriously concerned about the tool, then provide the friction factor and heat transfer coefficient for the tool. If I am more concerned on the workpiece material, provide the heat transfer coefficient and friction factor for the workpiece. So it is up to you to decide which I am going to study. I am going to study the tool or I am going to study the workpiece. So now I am going to leave as it is. Then next, the tool setup. The tool is also in the atmospheric initially, that is 30. Okay, then give next. So here at the top, now I am moving my cursor here. You can see I am completing step one by one. Okay, now there are two cases. I can import a geometry, that is a tool I have designed in SolidWorks or ProE that I can import. So what are the available formats? DB, IGS, DXF, then geometricals. Okay, so IGS file, DXF files, all these files are acceptable in this case. So here I am not going to import any geometry. I am going to design or define the geometry using the graphical user interface. Okay, so for this I have to click this define primitive geometry. Define primitive geometry. So here you can see these are the various shapes of inserts that is available, but this is the generalized shape of an insert. Where B, you can see it is the rack face, B is the rack face, C is the relief angle, R is the nose radius, and L1 and L2 are the length. If I want to change anything, that I can change here. I am going to change the relief angle to 3. Okay, similarly the nose radius, if I want, I can change here also. So according to my requirement, I am going to design or I am going to model the tool. Now create. Here you can see I have created. Now I am going to change this relief angle to 5. So now you can see the changes. So you can see now. So it is getting remodeled out. So nose radius I am going with 0.1. So here you can see the variations and all these things. Right? Now create and then close. Then I can also edit the geometries. So that all things now it is not required. Then next, this is an unquoted one. The insert that we have presently considered is unquoted. If I want to consider a quoting, tungsten carbide, for example, the base material for this insert is tungsten carbide, WC. If I want to quote it with TiAlN or SiC, then I can provide add. So here you can see what is the coating thickness that is required. 3. Material, what is the material? That I can consider. Coating with Al2O3, coating with titanium aluminum nitride, coating with TLC, coating with TiCN, coating with TiN. Okay. So these types of inserts or coated inserts are readily available in market. So that coated inserts also we can purchase and we can use it for experimentation. Okay. So at this point, I'm not going to consider this. I'm going to delete. So I'm staying with the uncoated insert. So here comes the tool mesh. The mesh generation is how you are going to discretize this total domain of tool. Okay. Where we have to consider finer meshing and where we have to consider coarse meshing. The point of contact of tool with the workpiece and the point of contact of tool with the chip has to be finer, and the parts that are away from this contact area should be coarser. Okay. And one more thing that we have seen in the morning is finer meshes increases the computational time, but at the same time the accuracy level will be higher. But whereas in the contrary, the coarse mesh, the accuracy level will be lower and the computational time will be less. So first I will go with this 700. I have taken 700 mesh size. Now generate mesh. Now generate mesh. Here you can see here the point of contact here. The mesh size is 0.0166, whereas here it is 0.1. The other part, the element size is 0.1. The element size is 0.1 mm or something for the units. So fine meshes are developed at the contact points, and the points that are away from here, it is going to have a coarse structure. So here you can see it is the rectangles, 4-noded rectangle or pentagon. Okay. Now I am going to change this to, for example, 5000. Now look at this size, 0.0167, 0.1. Now I have increased from 700 to 5000. I am going to increase. Generate mesh. So here you can see the size. Here you can see the size. More number of dense structure can be visualized. Okay. Then initially I will stick on with 500 for easy understanding. Generate mesh now. So next. So here we are setting the boundary conditions. We are setting the boundary conditions. So check here the temperature once again. Even though it is given as 30, check once again here. It is 30 now. Okay. Next. Insert material setup. Now we have to provide the material for this insert. So import material from library, import material from file, create new material. So I am going to import material from library. Here we have aluminum. So we have JS standards. Then beta materials, IN 718. Then dye materials. ASA H13 is a dye material. This is in DIN standards. Then others, tantalum, copper alloys and all these things. Then stainless steel, then steel, then superalloy. Okay, then tool materials. Now I am going to select steel. For this work, I am going to select steel. In this, the different steels that is available can be seen here. So in this, I am going to consider 1045. 1045. So this material is generally used in shafts. ASA 10 material is normally used in shafts. So now I have selected ASA 1045 machining ERC. ERC is nothing but Engineering Research Center. Engineering Research Center that has developed this model. Okay. Now here we can load, cancel and more. Now I am going to click more. Now here descriptions we can see name ASA 1045 machining ERC new, flow stress. So in the morning we have seen in the flow stress equation we will be considering strain rate and temperature. Okay, so all these values are taken here. So equivalent standard names. So flow stress comments, flow stress data from OSU ERC using modified JC equation, that is Johnson-Cook equation, JC equation. There is another thing, that is 1045 ERC. So there is no comment at all. So even though I am going to have some flow stress equations, and this is not specifically for machining. Okay, if it is specifically for machining, then this machining will be included in this. Then 1045 machining. So I am going with this 1045 machining ERC, which consider this Johnson-Cook equation. Okay, now I am going to load this. Sorry, because this is workpiece material. Sorry, the tool material should be tungsten carbide. Sorry, this is for workpiece. So the tool material is tungsten carbide. I am not considering any coating. So load. So this load is for material. Next. So here you can see the material is tungsten carbide, WC. Now I am going for the next procedure, workpiece setup. Whether we are going with the plastic or elastoplastic, I am going with the plastic. The temperature, the atmospheric temperature that we have considered is 30. So 30. Then next. Now we can import the geometry or we can define the primitive geometry. Here define. So here you can see. So this is this 2 dimension. So width and height. Now I am going to create. Now here you can see the model is developed here. Now I am going to change the height according to my wish. Now create. Now you can see here this will get changed. Create. So now I have changed this. So now I have created a component with a width of 3 and height 1. It may be centimeters or it may be millimeters, but the unit will be the same. Now close. So now the workpiece geometry I have created. Then next. So number of elements through uncut chip thickness. How many elements are there in the uncut chip thickness? Whether it is 25 or 40. Now first of all I start with the lower one. Red mesh. So here you can see. Here these components or these parts of the workpiece will not be in contact with the cutting tool initially. So these are all cores, whereas this is the point at which the workpiece will make contact with the cutting tool. So a finer mesh will produce here. Now, as a default, I am going to change it to 30. So now you can see the next. Once again, check the temperature here 30. So next. Now workpiece material. I am going to select this. ASI 1045 is my workpiece material. Okay. Then next. Then here we have manual positioning and generate default positioning. I am going to click generate default position. So now it has automatically aligned. So yellow is my workpiece and the blue is my cutting tool insert. Now it has made contact. Okay. Then next. Define model to calculate tool wear. So the tool wear is calculated based on the friction model. So in the friction model in the morning we have seen the Uzi friction model. Okay. So here you can see Uzi user defined. So I can also define a tool wear model. But for this I have to conduct higher experimental runs so that I can develop my own model. Okay. So use the tool wear model. Okay, for the so here you can see a manuscript here. For ASA 1045, the usual tool wear model, the constants A and B are taken these values. For Uzi tool wear model, previously some researchers have conducted experiments and they have determined the values for constant A and B, and that too for ASI 1045. That is, while machining 1045 steel, this will be the Uzi tool wear model constant values. So that I am going to consider. So 8078 and 5302. So I am going to provide point and the value of B is 5302. So what is the equation that we are going to use it here? So this equation dW by dt is a derivative equations. APBE. So that is A is nothing but the stress, ultimate stress, and volume P. Here you can see the sliding velocity and all these things. So here we have to determine only the constant A and B. Okay, so some researchers have done research on this and they have determined the constant values that I am going to select for my work. Then next, so number of simulation steps. Initially, I am going to consider it for 300 steps. Okay, how many steps to save? 10 steps. Length to cut. The total length that I am considering is 3. The width is 3. Okay, the width is 3 and height is 1. So 3 I have considered. In this off, I am going to consider here, or I can also give 2. That's not an issue. Okay, 2. This 300. I can stop with 100. I can stop with 500. What is the termination criteria? At some point, it has to terminate, no? So, which is first? If it reaches 300 iterations first, then it will stop. And before the 300 iterations, if the length of the cut has reached 2 mm, if the length of the cut has reached 2 mm, the simulation stops. The simulation stops based on the length of the cut or the number of simulation steps, whichever is earlier. So here steps increment save. Here we have a tab that is advanced. Click it. So these are all the simulation controls. So the name that we have given, parameter study, then operation name, units SI, deformation, heat transfer and all these things. Okay. In this, the grain sheeting diffusions, morning someone asked, some participant asked, so whether I can go with the microstructure and all these things. There is some other module in this deform 3D for microstructural studies that we can use. Okay, so Lagrangian incremental and then steady state machine. So in the 2D model, we are going to use Lagrangian model. That is, the element is fixed with the material. The morning we have seen Eulerian model, the element is spatially fixed. The Lagrangian model, the element is attached with the material. Okay, so here we are going to consider the Lagrangian incremental model. Then step function, second one, step function, number of steps that we are going to have. Then stopping criteria, that it is there, the die distance, stopping plane, then remesh criteria, the workpiece. Okay, tool also I can provide. Iterations, so direct iterations, there are two types of iterations, Newton-Raphson method, direct iterations. So I can also change here what type of iterations that I am going to form. So you can Google it, what is the difference between direct iteration and Newton-Raphson method. So optimization, you might have come across Newton-Raphson method. Okay, so that is the method in finite element simulations. Deformation, temperature, then process conditions, the environmental temperature. Now you can understand it. The environmental condition is 30 degrees centigrade. The convection coefficient, it depends on the material, the convection coefficient. Okay, then advanced, it is the error tolerance and all these things, just leave as it is. So, okay. Okay, now I am going to next. So now I have given the simulation controls. Now I am going to provide it as next. Database generation, status ready. Now I have to check my data. Once I click here, you come to the extreme left bottom. Here you can see the database can be generated. That should be the word that you should come. If your database cannot be generated, okay, unable to generate the database, it will be highlighted in red. When it comes like that, your model lacks some properties. So a model cannot be built in this. But in our case, presently, the database can be generated. So I am generating my database. So here you can see done writing database. At the bottom of the left side, you can see done writing database. So database is done. Now I'm not going to give next. I'm going to close operation. Okay, now I'm going to close the operation. Or I can open the operation. Straight away I can give here. So check database, generate database, yes. Next. Directly I can close or I can give next and then close. Do you want to close the current operation? Yes. So in a finite element simulation studies, we will be dealing that in three different parts. One is the post processing, then second one is the simulation, and the final one will be the post processing. Pre-processing, simulation, and then post processing. So the three tabs here you can see. Now after completing the pre-processing stage, the simulation and post-processing stage tabs will get highlighted out. Now I can going to click this tab, simulate. Okay, now I'm going to click this tab, simulate. So that is my operation, JER parametric study operation. Here simulate, we can have run simulation. I'm going to click this run simulation. The simulation has been submitted. Okay. So here you can see the nodal point, the iteration number, velocity, normalized, the relative velocity, and all these things. Here it is going to calculate. So if you want to simultaneously see, the simulation, here we come across the simulate, stop simulation, the process monitor, simulation graphics. I'm going to click the simulation graphics. So this will come. This window will pop out. Now here it is remeshing, that is adaptive meshing. Now I'm going to see the temperature. Here you can see the temperature. So 30 is my atmospheric temperature. Because of the machining, the temperature has raised to 231. I can also make it smooth, line, anything smooth I am going to make. So here you can go with the type of a display wireframe model, then shading, then solid model, then wireframe model, display boundaries. So I am going with the wireframe model. So here you can see the temperature. So 30 it is 395. So the 395 is little bit wide. So it is the temperature at the interface. So here you can see the metal is being removed. The metal is being removed. So here you can see now remeshing. Here you can see remeshing, that is adaptive remeshing. Because of the elemental distortions, new meshes will be developed. New meshes will be developed at the end. And that's why it is getting slower. So remeshing takes place. So this is two-dimensional analysis. That's why it is little bit fast. So now out of 300 simulations iterations, now I have reached 181. If I have gone for three-dimensional, then you might have ended with the 8 or 9 iterations only. So in the morning itself, we have seen if it is for try, if I'm going to make a try for simulation, or if I'm going with this, then obviously I want a lesser computational time, so I can go with the 2D. But chip morphologies and all these things we cannot study here. For this, we have to go only with three-dimensional machining simulation. Now you can see some material is being removed as chip, and it is in contact with the cutting tool. So here you can see now the program stopped negative Jacobian detector. That is, it is generating the Jacobian matrix. Normally in finite element analysis, we will be using this matrix, Jacobian matrix, for determining the variables. So that it is an inbuilt. So someone is asking, sir, what is type of mesh? Don't worry, get worried. The system itself will design and form by itself. So we have to make it finer or coarser depending upon our requirement. So the constant values the system itself will take. If I want, I can change or I can accept as it is. So now it is approaching towards 300 iterations. So two termination criteria. One, if it reaches 300, it has to stop, or if it reaches 2 millimeter, it has to stop. But from this, we can identify that the first 300 iterations, this simulation will stop. Now we have reached 290 iterations. So here also you can see the strain, how much it is straining, the strain rate, the stress, the velocity, the displacement, the temperature we can see. Now the simulation is completed. That's why you are not able to see the simulation graphics. Okay, now I'm going to cut it out. So here you can see a message. Simulation is completed and stopped at the user specified time step. That is 300 iterations. Now I have completed the pre-processing and then I have completed the simulation. Now I have to post-process. That is, I have to determine the variables from the simulation studies. Now post-processing. Okay, so here you can see. So these negative, minus 45, minus 90, minus 126. These are nothing but the places where the negative Jacobian matrix is obtained. Right. Now here you can see. Okay, there are some buttons that I am going to click it now, so that the animation can be seen. So now I clicked it. Now you can see the tool is constant and the workpiece is moving here. Workpiece is moving here. Now you can see it clearly. I will make it clear. So I will make it clear now. So I want to study the temperature. So here you can see the post, the state variables will be there here. The first D is nothing but the damage, then effective strain, then effective strain rate, then effective stress, then total velocity, then displacement, the normal pressure, temperature, and then this total setup. So I am going to click this setup. So here you can see what are the things that can be determined. The tool where also we can see the interface temperature we can see. Okay. So now I am going to click the interface temperature. Apply. Because now only it has contacted. There is no machining. So it is 0. Apply, close. Now I am going to run the simulation now. So here you can see now the interface temperature is raising. The interface temperature is raising. So interface temperature is raising now. Here you can see. So this temperature I can also determine. 1 second, I will go back. Now this temperature I have determined. I am going to determine. Here you can see the 30 is the atmospheric temperature. Now the machining started. Here you can see. So here you can see the change in the structure. So core structure is there. Sorry, fine structure is there near the deformation zones. Near the deformation zones, finer structures is there, and apart from them, coarsest fine grains are available. So this is how we are going to measure. Okay, if I want to measure the interface temperature, because the interface temperature plays a vital role. So interface temperature, apply. So in this case, the interface temperature is 406. Okay, and the overall temperature is 629, 630. Okay. Okay, because of friction and all these things. Then we can determine the damage, displacement, and all these things. Wear rate also we can determine. So this is the wear rate, because we have used the Uzi tool wear model. So for this material ASI 1045 steel, based on Uzi tool wear model, the wear rate is 0.0000121 millimeter per second. So that is the wear rate that occurs. Okay, close. Now here you can see the tools here. Here you can see the tools. This is the summary. So here in this case we can see the general, the deformation, the thermal, the heat treatment, the heat and all this thing, heating and all these things. So we are more concerned about these things. General, deformation, there it is the total strain, the stress. Here I can go for a graph, the mean principal stresses. So this is the minimum stress and this is the maximum stress. Minimum and maximum stress. So thermal. So this is the temperature. How the temperature is rising. How the temperature is rising. The temperature is still rising and it is not converging. The issue is I have stopped with the 300 iterations. So I have to go with the higher iteration steps so that this temperature will be higher or it is going to get converged out. Similarly, heat treatment and all these things we can see here. Okay, strain rate, effective strain rate is here, that we can give these graphs and all these things. So properties we can see. The title, if I want to give any title, I can give. AAER workshop I am going to give. Now I am going to change. So here you can see it is changed now. It is changed now. So here also you can change the decimal value, whether it is auto or significant to 3 decimals and all these things we can change. Close. So here you can see the graphs. What are the various graphs that we are going to have? The x-axis time and y-axis load apply. So here you can see x-axis time and y-axis is load. Okay, then energy apply. So energy is constant here. The x load apply. So here you can see. Here you can have force. Here you can have x force. So likewise, we can add. X-axis is time and y-axis is the energy or load predicted, x load, then y load. Okay, so similarly we can have this. How to import this graph? This graph data I have to import. So right click. So right click on the graph. Here you can see export graph data. Okay, export graph data, that I am going to grave it as graph. So it is nothing but a notepad. So here we can have all this data. By using this data, we can draw the graph now. We can have the graph now. Right. Cancel. So now I am going with the temperature. So whether this simulation is stopped with this? No. So for what we have done is we have simulated to the transient conditions. Transient conditions. So I have to predict things once the steady state is reached. Once the steady state is reached. Now how to do that? Once again I have to go with the pre-processing. Here you can see add operation, add digesters. So add operation I am going to click now. If I am going to click here, initially the operation number was 1. Here you can see now the operation number is changed to 2. But now this gets highlighted out. There is a drop down menu. Initially I cannot change this. That is, initially I have to perform the machining simulation only in the transient conditions. After doing the simulations, finally I have to move towards steady state. So now I am going to select the steady state. Now I am going to say the steady state. Now click open operation. Open operation I clicked. Then click next. Click next. Now the tool is not visible. The final chip that is produced from the workpiece is visible. So here we have a window, box zoom. So I am going to click this and I have to zoom only the chip. So now this is visible. So in the morning we have seen in the transient and steady state. In the steady state we have to do some changes in the chip. We have to remove a portion of the chip so that it becomes steady state. So how to do? Now this is a box zoom, this is dynamic zoom. So if I am going to give, then I can zoom it now. Okay, and this is pan that I can move here and there. Now here this is the select. Now I have to select this tool, arrow mark. I have to click any point on this chip, this point I am going to click. Then it becomes start. Then it becomes start. On the other side, if I am going to click this, it becomes stop. End. Start and end. If I click next, then this portion will be deleted from the chip. So then only the steady state condition can be obtained. Okay, now I have selected the start and then end. Now next, so number of nodes selected, you can see from here, free surface. The number of nodes is 16. So next, so here you can see the chip is removed. So here you can see the chip is removed here. Now the tool is visible. So number of simulation steps 20. It's default. It's default. Then click next. Once again check database. After clicking this, you have to see on the lower left corner. Then checking database can be generated. On seeing this only, you have to generate database. Here you can see now. Done writing database. Okay. Now next. Do you want to close? Yes. So now for the steady state condition, I have done the pre-processing procedures. The next thing is I have to simulate the machining process in the steady state condition. So simulate. Now run simulation. The simulation has been submitted. Okay. So 20 iterations I have given. In some cases, in the second iteration or third iteration itself, the steady state will be reached, and in some cases, error will be seen. Error. So then what we have to do is, once again I have to go back. Once again I have to go back and I have to run the steady state. So here you can see the program stopped by error. Okay, so 0 or negative value in log prediction. So it is not possible to run. So I have to select the previous one and then I have to run simulation. Error. So please go through preprocessor to process prepare data. That is, like this we cannot do. Once the simulation is stopped, we have to go back to the preprocessor and we have to modify there only, and after this we have to generate the database. Once a proper database is generated, then only we can simulate. So just like that we cannot simulate. That's why I click this here now. So once again I am going back to pre-processing. So this is, here you can see the difference. Now I am clicking here. At the end of the first operation, you can see first operation. At the end of the first operation, I am seeing here, you can see the shape of the chip. You can see the shape of the chip. It is not a cut chip. Now I am going with the second operation here. You can see the shape of the chip is different. So now I am going to open the next. So it is clear. So if I want, I can cut further. So I am going to select something here. So start and the end I am going to add. Then next. Then I am going with the 10. That I can also reduce. Next. Check data. So database can be generated here. Then generate database. Yes. Then next. Close the current operation. Yes. So similarly like this, we have to do again and again. Then simulate. Then run simulation. The simulation has been submitted. Okay. So once again there is an error. Why the error is occurring again and again? Because we have stopped with 300 iterations only. So enough chip is not produced. That's the first main thing. The first main thing is enough chip is not produced. So the problem exists, right? So consider now the steady state is reached. Then what to do? Then I am going with the post processing. I can determine the temperatures and all these things. So now only we have to determine. Now only we have to do the processing. So now here we can see the temperature is around 11,600. It is not at all possible because there is a error in the calculation. So I cannot click this. So I am going to click here. So 630. So once reaching the steady state only, we have to determine the variables. In the morning someone asks, what are the degrees of freedom? Here in this case, I am going to consider temperature, damage, strain rate, strain, then effective pressure, tool wear, cutting force. So at each and every element, we are, or at each and every node, we are going to calculate these variables. So the number of variables is equal to the number of degrees of freedom. Then now I am going to determine the cutting forces, or I am going to predict the cutting forces. So in this condition, what I am going to do is I am going with the pre. I am going with pre. So here the add operation, the add die stress is not highlighted. So I am going to just move this. I am going to just move. Now it is highlighted. So the add die stress, I am going to click. So die stress. Next tool, it is default is tool. Next number of extra die, there is only one die, so no extra die. Then die stress is isothermal. In the case of deformation, it is non-isothermal. If I am going with the die stress, it is isothermal. Next, the object is elastic in nature. Next, or if I want, I can select rigid. Then next, the next, check data, generate database. So here you can see no inter-object relations are defined. So here you can see database cannot be generated. So there is a problem in this. So once again I am going to back. So change it as elastic. Next. So here you can see once it has been changed to elastic, we are going to interpolate the forces. So geometry next. So here you can see force interpolation. So here you can see that is use system default value for contact generation tolerance. Yes, I'm going to use. So interpolate forces. When I click this, it will provide this. The forces have been interpolated from the workpiece to the die. Results. The workpiece, the cutting force Fx is 284 and Fy is 164, and in the die it is 279.33 and Fy it is 164 newtons. So thereby I am going to interpolate these cutting forces. So here you can visualize. So I am going with the box zoom. Then I go to visualize. So this is how the distribution is going to be. So at the exact contact of the cutting tool with the workpiece, higher amount of force will be exerted. As it moves on, the less forces will be there. So this is all about the two-dimensional one. Okay. So this I have done previously. Now you can take a look at that. Now we can take a look at that here. So simulate post processing. The temperature I am going to look into here. So now here you can see the chip is totally out. The chip is totally out here. Now I have done now I am going to go for the steady state condition now. So I am going to add operation. Now I am going to convert it into steady state. Then open. Then next. I am going to pick the node now. So from shear to shear. I am going to remove. So next. So here you can see the chip that is being removed. Then I am going with the 10 simulations. Next, check data, generate database. Then next, yes. Now I am going to simulate. So when the chip is closer or it is touching the tool, you cannot go with the steady state. That's the issue. So the problem is that should be enormous, some amount of chip that should be with the free surface. So now you can see here the steady state solution has converged. With how many iterations? This is 301. 6 iterations. I have given 10 iterations, but at the end of the 6th iteration itself, the steady state has converged because some amount of chip is away from the tool, so that the steady state is possible. So in the case of our example, instead of 300, if I might have given us 600 iterations, then the chip will be formation will be more, so the steady state conditions can be reached. So these are the things we have to take care of. Then post processing, so we can converge this into all these things, operations. So here you can see in the previous it was 11,000 something, but here you can see. So box zoom, here you can see how the temperature is. So here you can see the chip is out, it is not touching the tool. Now die stress, next, tool next, die stress is isothermal, then next, then interpolate force. So here is the force interpolation. So this is what we are going to do in the two-dimensional machining simulation in deform 3D. I hope that you can be able to perform the machining simulation studies using this deform 3D software on your own, because we have seen what are the issues that we can face. What happens when the database is not generated, how it will be intimated, when a correct steady state can be reached, that is the chip should be more and it should be away from the cutting tool, and all these things we have seen now. And now I will cut this and I will be moving towards the three-dimensional machining simulation. Okay. Now I am going with the 3D, that is three-dimensional machining simulation I am going to perform. So here, file, new project, So here the new project name is I am going to provide it as JAR Workshop 3D. Here also English and System International. So I am going with System International. Then next. Next, operation number 1. So here you can have the same type. It is machining transient condition. Machining transient conditions. Then next. So here you can see turning, milling, drilling, boring, all these machining conditions. All these machining conditions. But in the case of 2D, we can simulate only the turning process. But in the case of 3-dimensional, we can simulate these things. Turning, milling, drilling, boring, and all these things. Then next, here you can see in the 2-dimension the depth of cut is not visible, but in the case of 3-dimensional we can use the depth of cut. So surface speed I am going to change it to 200 meter per minute, and depth of cut is 0.3, and feed rate I am going with this same values. Then next, the environment I am going to change it to 30 degrees centigrade. So the coolant, if I am going to use coolant, what is the convection coefficient? For different coolants, we can use different, it will have different convection coefficients. If I am not going to use any coolant, then give it as 0. That is, I am going to consider it as a dry machining. That is, I am not going to use any coolants at all. Then next, the tool setup. The atmospheric temperature is 30, right? Then load an existing tool from library. That is pre-defined or pre-modeled tool I am going to use, or I can define a new tool. Define a new tool. So here you can see what are the available formats. .key, .db, STL files, geometrical files, PDA, and UNV files, Unigraphics files, and all these things. Okay, so I can develop the cutting tools in these softwares or in these formats, and I can also import it. But presently I am going to use an existing tool. So here you can see the inserts. Then DNA tool. You can see how these tools are changing. Then T, triangle tool. Here you can see what are the V. The shape changes. T stands for triangle. D, then C. So initially I am going to keep it as this thing. So the base material is tungsten carbide. So I am going to select this. Okay. Then next, tool holder. So for this I have to select a tool holder. For seed type insert, we also select these seed type tool holders, but in the database it is not there. So we have to generally select this one, the side cutting edge, the back rack angle, side rack angle, and all these things, and we have to give OK. So that this tool insert will be held on a cutting tool holder. So that we are going to assume. Now you can see relative mesh size 5000 to 50,000, right? So now for general purpose I am going with 5000. My model will not be accurate. So if I am going beyond to 50,000, then the accuracy level will be higher, but obviously the computational time will also be higher. The computational time will also be higher in this case. Then next, okay, now the meshing is done. Now I have to check whether the temperature is 20 or 30. But here you can see the temperature is 20. But what I have provided is 30. So once again we have to change this here. Then next, then workpiece setup. The temperature is 30. Next. So two different types I can change. I can create the workpiece. So this is the workpiece that is in the blue color that we are going to select. In the simplified model, the length I am going to give. Create geometry. So this is what it is being done. So this depth is based on the feed rate, or curved model I can generate, create geometry. So this can also be generated, but go with the simplified geometry. So back. So that's the problem here. Once we have developed it, right. Now next, so we can use the relative mesh size 5,000 to 8,000. So I am going with the lowest one, 5,000. Next, so automatically it will be generating. So here you can see how many elements are generated. So 1,002, 1,026 polygons and 551 points and all these things. So here you can see a finer mesh is seen here, and here it is coarse. But when the tool comes in contact and it moves further, these coarse grains will become finer grains. So that is the adaptive meshing. Next, so workpiece material setup. Import material from library. So steel, I am going with the AASI 1045 ERC. That one because it uses Johnson-Cook equation. Load, ERC. Next, so number of simulation steps. I will go with 100 because there is no enough time. So I am going with 100. So these steps also I can change 5. So arc length to cut 10 mm for example. So tool wear calculation with Uzi. So from this paper I have decided that I am going to give these values 1, 2, 4, 5, 6, 7, 8, 7, 8 and 5302. So the same advanced setup will also be there here. Okay. Then next, the status is ready. Check data. Database can be generated. It has to be seen here. Previously in the two-dimensional at the launch we have seen red color. If I see in that red color, there is some problem with our model. So we have to once again go back and we have to change it, and then a valid model has to be developed. Then generate database. Then next, do you want to close current operation? Yes, because I have completed my pre-processing procedure. Then I am going with the simulation. Then run simulation. The simulation has been submitted. Okay. Now I can also see the simulation graphics. Now this is moving faster. Actually in 3D, this will not move faster. But with the coarse grains, it is moving faster. Okay, when compared to that of the 2D, the computational time will be higher. Okay. It is not displaying because here it is remeshing. It is not simulating because the remeshing is going to take place. That's why I am not able to see the workpiece and the tool here. Once the remeshing is completed, then we can see the workpiece, and here you can see. So here you can see program stopped. So displacement, the temperature. So you can see everything. So now the temperature has raised to 201 degrees centigrade. So now I will stop with this because consider that it has 100 iterations. Okay, I have some other database, so I will load that. So this is the procedure of carrying out the initial transient condition in 3D machining. Okay, so now I will stop this and I will load a new one. Okay. So previously I have performed, now I am going to load that. Okay, so now I have simulated the machining in 3D. So post processing I am going to carry out. So here the zoom. So the temperature I am going to measure here. Now I am going to simulate. Now here you can see. So you can clearly see the chip formation. It is 1045 material. So we are going to have a continuous chip. If I provide higher feed rate and higher depth of cut, and depending upon the workpiece material that we are going to select, the type of chip produced will be higher, will be different. So now the chip is touching the workpiece. You can see the temperature changes there. The chip is touching the workpiece. So now the simulation has stopped. So now I have to once again I have to go back to pre and I have to convert this machining transient to steady state. So add operation. So this type I am going to change to steady state, then open, then next. Now, so this is my chip. Now I want to eliminate or I have to remove some portion of the chip, right? So here at presently number of nodes selected is 0. If I go to give this, press anything here, you can see apart from chip, all the workpiece material is selected. You can see at the nodes, all the nodes are selected. Why? Because presently the chip is touching the workpiece. That's why if I selected the chip, all the total workpieces is getting touched off. So what to do? Now close the operation. Okay. Now I am going to select a process that is before. Okay, now I am going to select a process that is before so that this will not touch the workpiece. So now I got a chip and it is not touching the workpiece. Now I am going with the add operation. So previously the chip was touching the workpiece. So for steady state condition, if I select the chip, the metal itself gets selected out, but it should not be like that. So the chip should not touch the workpiece. So one more thing that you have learned is the chip should not touch the workpiece. It should be a free surface. Yes. Steady state, open, then next. Now here you can see now. Now if I am selecting this, only the chip is selected. No material is selected. You can see now the nodes of the metal is not getting selected out. So 192. So next. So simulation steps, I will go with the 10 because there is no time. So next, check data. Database can be generated. Then generate database. Yes. Now close operation. Now simulate. Run simulation. Okay. And the simulation is running now. So what happens when this stuck on? We have to delete and you have to run once again. So that is the problem with this. Okay, this only produces a near approximation solutions. We can know how it behaves, but only the experimental results will provide with the better data for interpretation. But these simulations can be used to identify how a system behaves or how a machining process will be, what are the things that can be done, and what is the interface temperatures, what is the temperature rise in this case, and all these things. So someone may ask, so how the temperature can be determined during the experimental studies? Thermocouples can be used. So we have to mount thermocouples on the workpieces and then we have to do. But that is not possible because the workpiece is rotating. So what to do? In drilling and milling, we can plant the thermocouples on the workpiece because this workpiece was stationary. But in turning, we have to mount the thermocouples on the cutting tool insert. We have to mount the thermocouples on the cutting tool itself. Or in the other case, we can use IR thermometers, infrared thermometers, a non-contact type thermometer used for determining these temperatures. Metravit make is there, fluke make is there. Okay, there are many things that is available for measuring the temperatures in non-contact mode, but the precision level will be less than that of the contact type thermocouples. And most of the publishers won't suggest you to use that non-contact type because the accuracy level will be lower than that of the contact type thermocouples. So now it is converging towards this 275 iterations. Now it is reached, and now the iteration will stop. You have to check here below the simulation whether it is running or stopped. Still it is running. So now it is stopped because it has not reached this steady state condition yet, but the number of iterations has reached. Okay, now I have to go to post processing. Now I have to go with this. So now what is the temperature and all these things? So it is around 8,900 degrees centigrade. So the interface temperature that I am going to look into. So go with the tool where then interface temperature. You can go. So 4,390, but this is not possible. There is some problem. So here it is. So since the steady state is not reached, there is some problem in this. So here you can see the temperature ranges. So 521. So this is the correct one. Okay. Since it has not reached the steady state because of time duration, I have reduced the number of simulations to 10. So the steady state is not reached. Now, after reaching the steady state only, we have to go with the die stress. So once again, I am going to pre-processing, add a die stress. Then next, and next, because default it will be tool. Next, next, then isothermal, next, 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 interpolate force. So this is what? So Fx is 31 and Fy is 307 and Fz is 58. By squaring and adding and then taking the square root, we can determine the resultant cutting force. So once after reaching the steady state only, we have to calculate this dices, that is the cutting forces. So how the cutting forces are available here, that we can rotate and see. That I can rotate and see. So here you can see. Okay, the solid model will provide here. So the cutting forces are higher at the interfaces. The cutting forces are higher at the interfaces. So this is how we are going to simulate the machining process using deform 3D. So last thing that I want to show to you is, so we have defaultly taken the cutting tool inserts from the software during the process. So here I will create one thing. I'll move fast now, okay? Because these steps you know very well. Right. The tool setup. So previously I was loading a tool from the existing database. Now I have designed and modeled a new tool in SolidWorks or Pro E, somewhat in the modeling softwares, and now I have to import that. So I have to define a new tool. Now here I have one tool here, part 1. Right? That part 1, that the properties is it is a STL file, 3D object file. That is a STL file. So STL file I am going to load now. Okay, STL file I am going to load, open. Now here you can see my tool. Now I have to position that. Auto position and manual position 2 is there. Now I have to click this manual position and then click next. Okay. So manual position. So part open, manual position, next material is tungsten carbide, okay, load, next, yes, tool name, that I can finish, then next I'll go to 5000, but the problem is still it is not positioned properly. We'll see that in the last one. Next, the workpiece I am going to develop the geometry. Next, use relative mesh size 5000, next. So these kinds of different geometries you can see. So material is somewhat steel, some material is there. Next, so here you can see. So perfect alignment is not there. Perfect alignment is not there. So what to do? We have to go back to the tool setup. So here you can see what the tool setup or process conditions. Next, define a new tool, part, open. Now here you can see some x-axis, y-axis and z-axis, right? So manual position, click on any one of the axis here. Click any one of the axis here and just move next. It's not moving actually. So here it is. So here you can see the cutting face direction. So where is the cutting face? This is my cutting face, or this is my cutting face direction. So my cutting direction is changed. Right. So here you can see the nose radius. Now it is changed. Next, finish. Now next, tool holder, something I am going to select. So why I have selected this is how to position this newly developed tool with respect to the workpiece. So some axis we have to select. So there we have seen X, Y and Z axis. So depending upon our cutting edge, that axis has to be selected. So once you do once, you will get the practice to it. So create geometry. So now you can see a correct geometry is created. Now you can see the correct position of cutting tool on the workpiece. So what we are going to design, how we are importing, how we are positioning the tool on the workpiece, it's very, very important in this. So similarly, we have to carry out the simulations. So with this, we come to the end of the hands-on training session for this machining process simulation. So in conclusion, I'll conclude what has happened today. So in the morning session, we have seen some of the basics and the introduction about the machining process simulations. What are the assumptions that we are going to take? What are the models that is available? Okay, what are the materials model, flow stress model? Okay, that we have seen in the morning. And in the afternoon, we had some hands-on training for this machining process simulation using Deform 3D software for both the two-dimensional and three-dimensional machining process simulation. And in that, how to import a tool from a modeling software to the software, and how we are going to align and all these things, and how we are going to simulate the environment in transient conditions, and how to convert that into steady state conditions, and how we are going to interpolate the results that we have seen. And with this, we conclude to the end of this session. And I am very much thankful for all the participants who are joined with us for this 2 days workshop. And I have a hope that you all learned something about the importance of simulation studies and how to incorporate yours in this in your experimental and comparing it with the simulation studies. Okay, if you have any doubt, you can come back to the chat section, the question and the answer section. I will clarify your doubts. Until then, thank you.